Today we're going to talk about solutions and buffers. First we'll discuss where do solution recipes come from. Then we'll go through several common calculations required to make a buffer. I will cover preparing solutions. And finally, I will briefly discuss buffers that will be mainly a recap of what you've learned in biochemistry lecture. Solution recipes come from a variety of sources. The source you use depends on the application that you have. If you are working on a particular protein, or possibly a specific method, you may consult scientific literature as a starting point for your solutions in your experiment. If you're in a lab environment, an instructional lab environment, you may get your solutions from lab manuals. There are also a variety of professional lab manuals with standard methods and protocols published in them. Additional places that you may find solution recipes are handbooks, manufacturers and suppliers. Often certain assays and chemicals will come with a manual that has specific solutions outlined in the manuals. After much experience, you may also create your own buffers. In making a buffer solution, you first need to know how to calculate the concentration for that buffer or component of the solution. There are many expressions of concentration: mass per volume, molarity, percent, parts, molality, and normality. You should have already heard of all of these concentration expressions, so I want to go through how to calculate them in order for you to have accurate results in the lab. Mass to volume is used quite frequently in biochemistry. In particular, crystallography often reports their protein solution concentrations in mass to volume. It is the weight of solute divided by the total volume. For an example, 2 mg per ml proteinase K means that there are 2 mg of the protein in each ml of solution. For example, how much proteinase K is required to make 50 ml of solution at a concentration of 2 mg per ml? We can set this up as a proportion, since the overall concentration should be 2 mg per ml. If we have 50 ml, we can set it up such 2 mg or over 1 ml equals x over 50 ml. By rearranging the equation, you can calculate that x equals 100 mg. That is, there's 100 mg in 50 ml. Molarity is the concentration expression that most of you are used to using. Molarity is the number of moles of solute that are dissolved per liter of total solution. For example, a 1 molar solution of sulfuric acid contains 98.06 grams of sulfuric acid in 1 liter of total solution. To calculate how much solute is needed for a solution of a particular molarity and volume, you multiply the molecular weight times the molarity times the volume in order to gain the grams of solute needed to make that solution. Try this sample calculation. How much solute is required to make 300 ml of 0.8 molar calcium chloride? You can pause the video while you try the calculation. Now you've already completed the first few steps in making a buffer. You've found the molecular weight of the solute, you've determined the molarity and the volume desired, and you've determined how much solute is necessary by using the formula in the previous slide. Now it's just a few simple steps before you have the solution. Weigh out the amount of solute using a balance. You may use a weigh boat, or sometimes you'll actually use the vessel in which you'll make the solution, such as a beaker. Once you've weighed out the amount of solute that you've calculated you need, dissolve the solute in less than the desired volume. The solute actually has a volume, which will contribute to the overall volume. Once the solute has dissolved, place the solution in a graduated cylinder and fill to the volume you desire. This is often referred to as BTV, or bring to volume. Here's a schematic outlining the steps from the previous slide. 2 points that I would like to highlight are that the volume used in the initial dissolving of the solute is less than the desired volume, because the solute itself has a volume. Second is that although volumetric flasks are used in chemistry labs, graduated cylinders often replace them in the biochemistry laboratory. There are several ways to use percent as a concentration expression. Probably the most commonly used is weight to volume, which is the grams of solute per 100 ml total solution. This is very common use in biology. For instance, 20 grams of sodium chloride in 100 ml of total solution is a 20% weight to volume solution. Here's another example. How would you prepare 500 ml of a 5% weight to volume solution of sodium chloride? By definition, 5% equals 5 grams per 100 ml. Pause the video and do the calculation before seeing the answers. Weight to weight reports the mass of the solute over the mass of the solute plus solvent. Let's look at an example. How would you make 500 grams of a 5% solution of sodium chloride by weight to weight? 5% is 5 grams in 100 grams. 5% of 500 grams is 25 grams, which is the amount of sodium chloride that we need. We subtract the 25 grams for the 500 grams to get the amount of solvent needed, which would be 475 grams. So we dissolve 25 grams of sodium chloride in 475 grams of water. Note, we do not bring to volume. This is the total 500 grams that we would desire. Parts are sometimes used as concentration expressions. They are usually reported in ratios, such that a part would be 3 to 2 to 1. It is better to be clear what that ratio is, a molar ratio, a volume ratio, but for certain, all of the units for each of the numbers is the same. For instance, a solution of 3 to 2 to 1 of ethylene, chloroform, and isoamyl alcohol might combine 3 liters of ethylene, 2 liters of chloroform, and 1 liter of isoamyl alcohol, although these volumes are rather unrealistic. Parts per million and parts per billion are often used in environmental science and analytical chemistry. Parts per million is the number of parts of solute per 1 million parts of total solution. For instance, 5 ppm, parts per million, chlorine is 5 grams of chlorine in 1 million grams of solution, or 5 mg of chlorine in 1 million mg of solution. Parts per billion is the number of parts of solute per 1 billion parts of solution. Now that we've covered concentration expressions, I'd like to briefly review how we might make a buffer. First was outlined on the previous slides, in which you would make the desired volume and concentration directly. Second would be that you might make a concentrated solution that we'd call a stock solution is typically 10 to 100 times the concentration that you would use in an experiment. We may do this because it would save us time. If we're using similar buffer components and solution components in many different concentrations, if we had a stock, we would not need to make each solution every time and go to the balance and pH our solutions every time we needed a solution. So by making stock solutions, we save time in the lab. Once you've made a stock concentration, you then use the equation C1 times V1 equals C2 times V2. For instance, how would you prepare a liter of a 1 molar solution of tris buffer from a 3 molar stock of tris buffer? The concentrated solution is 3 molar, which we would designate as C1, concentration 1. The volume of the stock needed is unknown and is V1. So if we set up the equation, it's 3 molar times X equals 1 molar times a liter. Make sure you watch your units, since molar is in moles per liter. So if we do the calculation, we calculate that we need 333.33 mils of the stock solution of the 3 molar tris. Now it's always good to think in common sense. We wanted a 1 molar and our stock was 3 molar. So 1 is a third of 3. So our volume makes sense because 330 mils is a third of a liter. To make the solution, we would take 333.33 mils of the concentrated stock in a graduated cylinder, and then we would bring to volume with water to 1 liter. In terms of buffering capacity, remember that diluting the buffer does not change the pH. However, the concentration of buffer does have an effect on the buffering capacity. Sometimes stock solutions are reported in terms of X. The X is how many more times the stock is than the working concentration. You generally want to dilute such a stock to 1X. So for example, a stock of SDS labeling buffer is labeled 4X. How would you use the stock solution to dilute your 15 microliter protein solution to load on a gel? We set up this equation using the C1V1 C2V2 relationship. So 4X is the concentration of solution 1. V1 is unknown, that's how much of that stock we want to add. C2 is 1X, that is the working concentration, the concentration we desire. And V2 is 15 microliters of our solution plus whatever volume we add of the labeling buffer. So solving for X, we get 5 microliters. Be sure that you're very comfortable with using this type of calculation. So you would add 5 microliters of the SDS loading buffer and 15 microliters of your protein solution. Again, it's always good to double check that things make sense. So if your SDS labeling buffer is 4X and your total volume that you've calculated is 20 microliters, 20 divided by 4 is 5, and 5 is the amount of SDS loading buffer that you're using. Here's an example for you to try. You made a 100X stock solution of lysozyme. How much should you add to your 1-liter buffer? Pause the video so that you can do the calculation before you see the answer. Here are a few tips to assure the quality of the solutions that you make. Documentation, labeling, and recording what you have done is very important. It's important to document in your notebook and also to write with labeling tape on the glassware that you are using exactly what it is you are making. Be sure to use labeling tape. Please do not write directly on the glassware. Writing out detailed standards of procedures or SOPs is also a really great way of maintaining reproducibility in your buffer making. Be sure to maintain and calibrate the instruments that you need, both balances and pH meters. And be sure that the chemicals you are using are stable, have been stored in the proper environment as indicated on the bottles, and are being used before their expiration dates. You should already have a good concept of what a buffer is based on your general chemistry and biochemistry lectures. However, I will briefly highlight the terms and concepts that you should know for this laboratory. Also in the assigned readings is some refresher, and you can consult your biochemistry textbook for additional references. So buffers at pH values around their pKa values are solutions that resist changes in pH as acid and base are added. The plot of pH versus base or acid added is flat near the pKa as shown in the figure below. Buffers are used to maintain a pH of a solution, especially one in which a reaction is occurring in, such as your enzymatic reaction. You should be familiar with what a pK is and some common pKa values for buffers that are commonly used in the biochemistry lab. You should be able to use and apply the Henderson-Hasselbalch equation to any calculation put forth. There are several examples in your textbook for the laboratory on page 55 through 59, as well as additional examples on 61. To refresh your memory, here are some equations related to basic equilibria expressions. You should be familiar with the equilibrium constant and how the relationship of the products of reactants of an equilibria relate to that equilibrium constant. You should be able to manipulate this equation to generate the Henderson-Hasselbalch equation, and you should be able to use this Henderson-Hasselbalch equation for calculations. Many buffers are polyprotic, and you should be able to understand what that means and what the individual pKa's provide in terms of buffering capacity. Here are a few buffers commonly used in the biochemistry laboratory. You should be familiar with some of these and their pKa's, as well as a list on page 60. One last note to consider. Some pKa's of buffers are temperature sensitive, so that the buffering range and pH at room temperature is different than that at 40 degrees Celsius. Tris buffer, which is a widely used buffer in a biochemistry lab, is sensitive to temperature.